Good morning or good afternoon, depending on where you're calling from. My name is Charlotte, and I want to welcome you to today's webinar, Getting Started with Stream Processing. Before we begin, we have a couple housekeeping items to go over. Everyone will be muted for the webinar, so please type any questions you may have as we go along into the Q&A panel, and we'll answer as many as we can at the end of the presentation. Also, this webinar is being recorded and will be sent to everyone via email following the webinar. Now that we've got that taken care of, I want to thank you all again for joining today's webinar, Getting Started with Stream Processing, presented by Ben Evans. Ben Evans is a distinguished engineer who has worked across the industry. He is a Java champion, author of 4 books, and spent 6 years serving on the Java Standards Committee. He's worked as an independent expert to Hazelcast for several years and has authored some of our most technical white papers. And with that, I'll pass it off to you, Ben.
Thank you, Charlotte. Just unmuting myself there. I hope everyone can hear me okay. If there are any problems, then please let Charlotte know. Thank you for that kind introduction, and let's get started. I'm really pleased to see so many people online today. So what we're going to do today is, first of all, I'm going to introduce myself and just give you a little bit more of my background. And then we're going to talk about stream processing and really where some of the ideas come from. And basically why we think that stream processing is going to be an important feature of enterprise architecture and why it's becoming so prominent in the industry today. After that, we'll move on to talk about Hazelcast Jet. I'm going to try to keep the slides to pretty much as much of a minimum as I can, and instead try to stay in the IDE for as much of the hour as we possibly can. I think we'll probably do about 45 minutes to 50 minutes of slides and IDE demo, and I want to leave some time for your questions at the end. So let's get started. So I'm Ben Evans. As Charlotte says, I've done a bunch of things within the community, including Java Champion and the Java community process. I've also worked extensively with the London Java community, which is where I'm speaking to you from today. And I've been serving on the organising team there for more years than I care to think about. I've also worked extensively in the charity sector and helping to provide skills across the world, including most recently for Global Code in Ghana. On a professional front, I'm the CTO of a new startup called Giftcoin. I've previously founded a company called JClarity with Martin Verberg and Pepperdine. Further back in my career, I was at Deutsche Bank and Morgan Stanley for many years. And before then, and the reason I mentioned this last one is it's going to be relevant to one of the examples I'm going to talk about in about half an hour's time, which is Sporting Bet, and we'll see why that's relevant in a bit. Okay, so enough about me. I should also introduce Hazelcast and Hazelcast products. Now, this is kind of interesting because people sometimes get a little bit confused by Hazelcast. They started life, they're an open source company, and they're most famous for a product which we actually call Hazelcast IMDG. And IMDG here stands for In-Memory Data Grid. It's essentially a large cache which is distributed across machines, typically over a local area network or even over a wide area network, which acts as a coherent cache, which is used to do some processing in memory, but mostly caching. And the company name has kind of become synonymous with this product. The product that we're going to talk about a bit later on is actually a completely new product, which isn't a cache, but instead is a general stream processing engine, and that's called Hazelcast Jet. So some people sometimes muddle up the company and the product. So I thought it was good to just mention that there are actually 2 distinct products, both open source, both with an enterprise edition as well. But in general, if you're looking for information about Jet, be a bit careful, because if you just type Hazelcast into a search engine, what you're going to get back is it might well be the cache product rather than the actual stream processing engine. Okay. So with myself and the company introduced, let's actually see if I can swap and bring up the IDE. I need to share a different screen at this point as well. Okay, so Okay, so hopefully at this point you can see my IntelliJ screen and not the Keynote screen, because otherwise it'd be too small. So what we're looking at here is something that we're going to look at in a lot more detail later on. But I just wanted to kind of start by motivating the discussion about stream processing. In order to do that, I really want to talk a little bit about the Java 8 Streams API. Now, don't worry too much about the domain model that we're looking at here. It's actually from an example called BetLeopard, which we'll be talking about in a bit. But instead, I just want to focus on this piece of code here. So this is a very simple bit of straightforward Java, and we're using the NIO2 API here to use the standard get class loader trick to get back a resource which ships within the bundle or the jar that the application has come in. And I've converted it to a URI, fed it into paths, basically to allow myself to have access to a simple bit of resource of test data that I've shipped with this piece of code. I've then converted it using the Files API into a list of string, and then we're going to do some fairly standard, pretty traditional Java 8 streams code on that. What we're going to do is we have some domain objects which are called horse, which are representative of a racehorse, and an event. And an event basically is a race meeting or a collection of races that the horse might participate in. And this application actually is a simple horse racing betting engine. So what we're going to do is we're going to generate a map which has as its keys the events and as its values the horses. And what this is going to represent is it's going to represent any horse which wins a race or wins an event, if you like. So this is a fairly simple use case for Java 8 streams. We're going to take the incoming list that we have of events, and we're going to turn it into a stream. Now, in that file are actually individual pieces of JSON. So what we're going to want to do is to take the JSON out of the file, and one line at a time, we're going to use this map transformation here to take in the piece of JSON and pass it to a JSON parsing function. So that basically is going to take the JSON representation of the event and turn it back into an event for us. Okay. Having done that, we're then going to pass it into a collector and basically use this to basically convert it back into a statically typed map for us. Now, this type of coding is I would hope very, very familiar to people who've worked with the Java Streams API. And there's something about the Streams API as opposed to the Collections API that you might never have noticed. And it's kind of this, that the Java collections have within them a design feature or a design principle that is not all that explicit. Java collections, when you deal with them, you have one object which represents the collection, and you also have, from that initial collection object, that is going to hold references, directly or indirectly, to every element which is present within the collection. Okay? So think about that. If you have a Java util list, then the implementations of that you might expect are maybe array list or maybe linked list. And in the case of array list, you have a reference to the array list, and that has internally an array of objects, and that array will have references to each object that's in the collection. Now that's okay as a representation goes for the aggregate, which is the list, but it has certain limitations. First of all, it means that you have to be able to hold all of the elements of the list into memory at once. You could think up some very clever implementation of list rather than the array list, which actually loaded the elements on demand perhaps or generated them, but there's still that assumption present in there that all of the elements are kind of reachable. Now, streams don't really have that. One of the core aims of the Java util stream is to say, okay, well, streams are kind of a use-on-demand concept. We don't actually have a reference to everything which is present within the stream. What we want to do is we want to define a way of doing some processing on the aggregate without really having to actually specify that we have references to each element as we go. Instead, we're going to use the stream as a template temporary abstraction, which is used once. So we're going to let the elements flow through the processing pipeline that we have, and we'll deal with the elements as they come through. And then after we've done that, the stream abstraction is over, and that stream object is not actually reusable. Now that is actually a really quite a powerful departure, because what it now means is that we can actually we can potentially think a bit bigger. If we have these streams rather than the collections, well, does it matter how big our data sets are? Well, not really. Could we, for example, write an implementation of stream which, let's say, watched a log file and just as new lines turned up, passed new things into the stream for processing? Could we have a stream that was generated by a piece of code? For example, the stream of all prime numbers. Is that something we could generate? Well, potentially, yes. So the stream abstraction is more general, and it also opens us to possibilities of how we manipulate data beyond just using collections. So that's, I think, one of the reasons why it's a powerful abstraction and why it's starting to make additional headway into enterprise applications. Because as our architectures become more complex, we definitely find that there are sources of data which are too big to be handled by just slurping it all into a Java collection and dealing with it. So streams, do have some of the properties that we want for building larger and more robust and more scalable enterprise architectures. But of course, Java streams have one particular problem, and that is they're limited to a single JVM. So no matter how useful that abstraction is, we do still have some fairly hard limits on how we're going to work with it. Let's suppose we'll take the example of log files again. Let's suppose that we're looking at the incoming log lines from your web plant. Let's suppose that we're going to analyze the HTTP response codes that you've put into your server logs. Because let's suppose you're building a monitoring system or some kind of early warning. If you suddenly start seeing a lot of 404 requests or 500 response codes, you know that something's wrong in your plant. Okay, well, as your web plant gets bigger, it's unlikely that all of those log lines are going to be able to be processed by a single JVM anymore. But then you start to have problems that, okay, well, how do we parcel out the log files? Do we have one log ingester per web machine that we've got? Or maybe we need to do something smarter. So where modern stream processing has really come from is an attempt to take the idea of that streams represent and to do it in a way which is also extensible to distributed computing, so that we want to have not only stream-based processing but also distributed. So the ideas that we're already familiar with from Java 8 streams, things like, let's say, the use of functional programming, so that we have maps and filters, and what they're going to do is they're going to take in a functional operation or a predicate or another type of functional or lambda-based approach, and that they're going to be used within the distributed streams that we're going to build. There are some caveats here. I'll come back and talk about some of those later on. But one of the ones which we should probably mention now is if we just open up the map API on stream and come into function. This is the primary function interface, which is present within Java util function. And there's probably something here that you may not have noticed before. And that is that the function interface itself does not extend serializable. Okay? So serializable is going to be necessary if we're going to build distributed versions of our pipelines. If you remember, just in case anyone's confused by this, let me just. Let me just make this change elsewhere. serializable interface is going to be necessary. Otherwise, we won't be able to take instances that we've created on one of our distributed nodes and move them to another node. That, of course, is a marker interface, as you can see. So in case you were confused about how function could extend serializable and still remain a functional interface and still eligible for use in Lambda expressions, well, actually, don't forget that serializable is a marker interface, so it would be possible. However, for some deep technical reasons, when the Java 8 Lambdas project was running, it was decided not to make function actually a serializable interface. There's some very interesting stuff to do with how Lambdas are actually implemented as to why that decision was made. But for our purposes of wanting to do stream processing across distributed nodes, we are going to need serialization as well. Okay, so let's come back to Keynote. And now that we've kind of motivated moving beyond the Java Streams API and into thinking about distributed processing, let's introduce Jet. So Jet is, I would describe it as more of a next generation stream processing engine. It's built on Hazelcast IMDG. You see, even the companies themselves occasionally do conflate the company name and the IMDG name. And it's based on what are called the DAG model. And DAG stands for Distributed Directed Acyclic Graphs. And that, it sounds scary. It's actually a piece of mathematical terminology. And what it means is that there are some flows, and the flows through the graph cannot go in circles. That basically there might be forks in the flow, but ultimately the forks can't go round in a loop. And that basically has a nice property, and the mathematics underneath this basically mean that there are some nice mathematical properties based on this that we want to have. And it's worth noting that the traditional Java util streams actually provide a much simpler set of flows than DAGs actually allow for. So one of the things that we've got by moving from Java util streams into the distributed world and to come up to the DAG model is that we're actually capable of doing some more complex processing than is typically possible. So let's see some of this in action. Okay, a few more details about Jet. It started in 2015, and the first release was February last year, which is about when I started looking at it. It's a JVM technology based on Java 8 and upwards, and it's fully integrated with IMDG. And for I think all of the examples I'm going to show today, we're going to use Hazelcast IMDG as a data source and also as sink for Jet. No, actually, I tell a lie. We do actually have one example which uses a different source to IMDG. One of the things which is important to notice is that this is sometimes called a true streaming approach, which means that in terms of the non-functional requirements that the architect might think about when considering Jet cares first and foremost about latency. It wants to deal with handling processing in real time with as low latency as possible. Now, it turns out that the architecture of Jet is actually very suitable for providing some good throughput as well, but it's not the primary concern. The primary concern of Jet is latency, and rather than something like Hadoop, for example, where Hadoop cares about producing more long-running queries over maybe a huge data set, and is so very concerned about how much throughput it can put through, and how quickly and how efficiently it can execute. With Jet, what matters is the timeliness of the answers that it can give you. But having said that, there are also what are called controllable delivery guarantees. And what that means is some of the people on the line might be familiar with what's called the CAT theorem for databases. And it turns out that there is actually an equivalent of the CAT theorem for messaging. And Hazelcast allows you to, within the constraints of that theorem about how reliable you want delivery to be, Hazelcast can give you some more advanced controlling if you need to. Overall, the pipeline looks like this. Over here on the left, we have some technical sources, IMDGs at the top. You can also pull data from things like Kafka, from JMS, either from JDBC or other, including NoSQL databases, or you can do files. So if you want to watch a log file, or you can pull from HDFS if you want to, and there are also sockets as well. Once you've actually identified your data source, and of course one of the nice advanced use cases for Jet is being able to pull in data from a whole bunch of different sources. So you could combine, for example, JDBC and flat file events. You could pull in all sorts of different sources in combination, and basically build up a very rich picture of your application by combining several sources. You ingest the data, you can stream it for things like Kafka and flat files. You can even define windowing, which basically is the ability to handle events in let's say a 10-second chunk, a second at a time, that you can transform the data and then pass it off for computation, which is normally done distributed and in parallel. There's also a powerful combination API, which you can think of as the group by equivalent, or the collection part of the Java Util Streams API. But a whole bunch of the things which are interesting about Jet, you can't really do until you recognize the fact that you're in a distributed world. I've tried to draw a lot of connections and similarities between Java Util Stream and Hazelcast Jet, and in general stream processing. But the truth is that for any good distributed stream processing model, once you get past a certain point of complexity in your thinking, then there are effects which come about because of the distributed nature, which don't really have any parallel in the Streams API. So Java Util Stream is a good initial mental model, but it doesn't tell the whole story. And as you work with stream processing, at some point you actually have to face up to the fact that what you're dealing with is the distributed grid for processing, and that there are certain things where you just can't hide that nature from the end user developer. So that's something to think about as you get more used to stream processing. Under the hood, we have this distributed Java Util Stream model, which is kind of in the background there, which is why it's slightly shaded on the slide. And jobs will be submitted to a manager. They'll be passed into, and this is just a generalization, of course, of the traditional map reduce job, where you have filter nodes, which will forward on to map nodes, and will all forward on to a reduce. So you could think of this as being I guess, similar to a parallel stream in the Java Util Stream sense. But of course, with Jet or with any other stream-based processor, this can be distributed across machines. So this is not restricted to a single JVM, and instead can be run across machines. Okay, so from an architectural point of view, when we want to design a piece of stream processing, how will it work? Well, the data items will flow through the DAG, just as they would flow through a stream. We should make sure that the transformations, so any maps or combinations or reduces or any other operations that we have, filters, for example, they should all be functional. Now, that means really two things. They should definitely not involve any state. So they should be immutable functional objects. And the processing of an individual transformation must complete in bounded time. Now, what I mean is that you shouldn't write a lambda or a function object and just decide that it's going to have a loop in it. Generally speaking, with any kind of processing Java Util Stream or anything which is using a lambda, if you find yourself using either a lot of state or having loops within the body of lambdas or other function objects, then that's generally a bad sign. What's more important for Jet and for other stream processors than for Java Util Stream, you must avoid a single-threaded pinch point. So this is an analogy in the stream case would be something like the sorted method. You can generate sorted streams, but if you try to do so, then what will happen is you will force all of the elements of the stream through an individual point, and you typically don't want that. In the distributed case, what you don't want is to have to ship the entire data set to a single node for processing. So that can happen if you don't have a function which partitions the data when grouping, for example. Now that is a kind of a gotcha which is present. It's one of these areas that I mentioned earlier that you can't really ignore the distributed nature of stream processing. At some point, you actually have to face up for it, and you have to be careful not to do anything which is going to destroy the distributed nature. Also, remember that the flows for Jet and for other DAG-based processors will be more complex than for Java util stream. The ones I'm going to show today, I think, are pretty simple still, but it is possible to build more complex examples, which is both good and bad. Now, fortunately, Jet has a nice checker for the pipelines that we're going to build. And if the pipeline doesn't make any sense, e.g. if it doesn't have a flow all the way through it, or if it has orphaned nodes within the pipeline graph that you build, then Jet will give you an error. So it's, you can build more complex things, but there are some basic sanity checks and some safety built in. We talked about the sources and sinks earlier, but here's a quick list of all of the ones which are present. As of the latest version 0.6, you can even implement your own source if the menu of available ones isn't quite where you want it to be. Just before we actually meet some of these APIs, I just want to mention that there are really three main APIs that Jet provides. There's the Pipelines API, which is, in my opinion, by far the easiest to get started with. It's the one that I tend to use unless I have to do something which is really not possible from within it. Then there is the low-level DAG, or sometimes called the Processor API or the Core API. This provides you with full power to access everything which Jet can do, but it's quite low level, and it can be hard to think about. It's a different model than developers are used to thinking about, especially if they're coming from a streams background. But the DAG requires you to actually kind of build the object graph of how the flow is going to work in your head, and it can be a little tricky to think about. There's also a distributed Java util stream API. Because of the drawbacks of how streams are actually different from distributed stream processing, I would say this API is probably less important. It's not quite deprecated, but in general, you can do everything which you could do with that from within pipelines, and the pipelines are just much nicer to work with, I think. Okay, so let's meet BetLeopard. We had a quick preview of this guy earlier on. It provides us with a simple domain model for talking about horse racing. Here are the event and the horse that we had set up earlier. We have some other typical things within a horse race that you might expect, that you have bets. And a bet, by the way, for people that aren't familiar with horse racing, is either a single bet where you just bet on a horse to win a race, or it can be what's called an accumulator. We have several bets which are linked together. And if you win the first bet, the money you won from it goes on to the second horse, and so on and so on and so on. So there are some interesting little complications in the domain model here. For example, some of the fields here are optional, and some of the things, there's not a simple one-to-one relationship between some of the data items here. It just helps make it a little interesting, and it provides for a slightly richer domain example. It's available online, so if you want to have a look at this and see how to use BetLeopard as an example of a distributed sportsbook, and it basically comes from a time when we were working to showcase IMDG and some of the initial stream processing that we were starting to think about doing. It's a good use case for IMDG and how it applies to domain models. So let's meet his updated cousin, JetLeopard, who, as you can see, has now sported a nice World War II flying helmet here because he's now flying a jet. So let's have a look at that. This is also present in the main repo, where we're going to be able to find all the demos I'm going to talk about today, which is under Hazelcast Jet demos. And this basically shows us a first kind of real-time performance stack. And stop sharing Keynote. Okay. before we get into that, let me just show you a slightly simpler example. So this basically is the same analysis that we were just looking at a bit of with the Java 8 Java util streams approach. And I kind of like this because it shows you the simple layout for a Jet application. Within the main function here, we're just spinning up our main class, which is analysis Jet. We do a setup, and then we do a go. The setup involves a slightly more Jet orientated or Jet version of that same initial idea, that we pull the resource file that we need out of our own bundle. We do that here with a bit of idiomatic Java 7, and then just use the for each API to basically put all of the data from that into this name to event. And name to event is just a Hazelcast IMDG map that we've got back from Jet. So Jet provides access to underlying IMDG maps if it needs them. So we basically load up everything that was in that JSON file and put it all in this map that we're going to use later on. Having done that, the whole of the Jet job is handled with just 5 lines of code, and 2 of them are println statements. So what do? Well, we just print the startup message, log the nano time, we build a pipeline, we pass it to Jet via the new job command. Remember that Jet is just this new Jet instance. We join on it because Jet executes asynchronously. So if we actually just want to wait for the result of the job, we just join against the job that we've just created. So it really is that simple. All that we need to do is we need to call this method on Jet, which is called new job, with this pipeline object, and then wait for results. So the simple steps are: load the data into IMDG, build a pipeline, execute it, and join on it. And that's all that's really needed. A typical pipeline is one like we might create here. Again, the structure of this method is really, really simple. We do pipeline create, and then we return at the end the pipeline that we've built. Each step, we take the step before, and then we determine what we're going to do with each step. So for the initial pipeline, we do a draw from, which basically indicates the data source that we will use. And at the end, we'll do a drain to, which tells us where we write the data back to. So where are we going to be drawing from? There's a helper class called sources, which will be our map name. So that will be our Hazelcast IMDG map. We then have a function, which I've just written as this very simple predicate. And this one is T, which always returns true. This is an input filter. So what we're going to be doing here is simply saying which elements from the map we want to include in our initial pipeline calculation. It's good to do this because what it means is that if there are any events that we know or any items in the map that we know that we don't want, we can exclude them before they ever enter into the pipeline. So it's just a simple performance optimization. In our case, we set just return true always, so we're going to include the whole map. And then we have the horse from event, which is a simple transformation function. So all this does is it takes the incoming event and it selects the winner. Okay. Now on the next line down, we actually have a notice that the type here is what's called a batch stage. If people have encountered Spark, this is the broadly equivalent to an RDD in Spark. And the idea behind it is that essentially it provides an intermediate step in the calculation that we will ultimately resolve on the final line here. This one's really simple. We just take the whole item that we've generated, which is just a horse, and then we aggregate it into a counting. And the counting method basically is just a straightforward accumulator, which is going to count how many of these have ever been seen. And then after here, we've got a simple filter, which will work just like a util stream filter to say only include the ones which have been seen more than once. So what this will do, when taken together, is it's a simple pipeline which any items that have been seen more than once. Or to put it in other words, any horses that won more than one racing event. So all of this is really just simple functional programming. A couple of the method names and a couple of the concepts are slightly different, but actually there's not a whole lot here which should be too dissimilar to what we do with regular Java util streams. Let me show the JetLeopard in a bit more detail. There's some boilerplate in here about setting up some constructors and some Hazelcast maps in order to build some holders for our objects. That's essentially boilerplate. We also have some methods where we just basically preload a load of random data, just so we've got some interesting things to show. But the main meat of this application happens in run, and this will run indefinitely while not shut down. And we take the simulated bets, add in some new bets into the betting engine. So this shows you how Jet can work in real time, because we're just adding more information into the betting engine within each loop here. And notice that the pipeline object was actually pre-calculated once in the init method. That's because the pipelines are actually not like Java 8 streams. A Java 8 stream is consumed when you use it. You only use it once. It can't be reused. Whereas a pipeline actually does represent effectively an abstract model of the processing to be done. So you can actually reuse it as many times as you like, because it's really nothing more than an immutable description of what is to be done. So it represents the processing pipeline, not the state of a stream that is currently being used. So it's a slightly different usage. And then after each step, we recalculate, and to make it easier, I've done this one as a synchronous join as well. And then we also, once we've done that, at each step, we output the losses. So let me just show you how the pipeline building works. This is a much simpler one. A slightly more complex one than the simple one we saw before. But it's the same idea again. We create a pipeline, we draw it from the IMDG source, and then we write it back to a map at the end. The difference is really these two stages here, where we actually do some slightly more advanced functional programming. But again, the methods we're calling here are things like flatmap. And the first step is to take a user and figure out how many bets they have. And what we want is to end up with a tuple 3, which is a type which doesn't exist in the JDK. So it has to be supplied by Hazelcast. So that the Hazelcast Jet data model actually has a type called tuple 3, which is used. So we're going to take a user and we're going to convert it into a stream of tuple 3s, and then the flat part of the flat map will then turn that back into this batch stage. So just a simple piece of functional trickery, really. We take the user's bets and turn them into a stream, filter out anything so that we're only using with single bets, and then turn them into these tuples. So far, so good. And then from that stream of tuples, or batch stage of tuples, we're then going to convert it, turn it into a different form, which is for each race, the projected loss if each horse was to win. So what that means is that let's now talk about the space of, no matter what state of races occurs, we now have a set of calculations which indicates what the losses will potentially be. This now means, having put all that information about the risk model, because this is really what we're building here, we're building a risk engine which indicates how much the bookmaker is potentially exposed to. We can then just produce from a simple piece of functional programming. Well, it looks a little complicated, but it's actually not that bad if you step through it. We can actually produce a final worst case scenario. So for any combination of horses winning various races, there's going to be a worst case scenario for the bookmaker, which is the perfect storm of which causes the worst losses that could happen. So let's see this running. Okay, so I've just brought this up in the IDE. Okay, it's done already. So what we can see here is, first of all, there's just some debug information where we entered the horses. We checked that we had 100 users and 100 bets. Because I've started this up, we can actually see the results of the pipeline calls we got. And we've got the vertices and the edges and a description of the graph that we built using the pipelines. Okay, and then we calculated the outputs. And we can see that with one event and 100 users and 200 bets, our worst case total losses were that. Oh, and then we ran it again. And now you can see that there were 300 bets, and the potential losses are getting worse and worse. So all of this is continuing to happen in real time. We have a simulation of more bets being added, and the risks are adjusting as the application runs. So that basically we can do this. I've done it as a delayed model, where we're seeing a 20-second gap between the recalculation each time, but that's just because this is a first example, and it will actually work equally well in real. Okay, I hope I've just unmuted myself again. Just hit the wrong button. Okay, so where we're slightly tight on time. So that's JetLeopard. Please download it and have a play with it. It should work fine in Java 8. The next one that I want to show briefly is a Twitter sentiment analysis. So this actually, I tried this last night and have discovered that thank you Twitter, Twitter have actually changed their API, so that now in order to connect to Twitter, you actually need to do a pre-registration process, which actually takes several days or a week. So I wasn't actually able to get new credentials, which would make this work. So I'll just have to show you the code without running it, I'm afraid. The idea behind this application is that it's a sentiment analyzer. What that means is that it will connect to Twitter and treat Twitter as an endless stream of new tweets, and it will analyze and look through them and look for tweets to do with cryptocurrencies like Bitcoin or Ethereum. And it will take those tweets and it will analyze them using what's called a Stanford Core NLP. NLP here stands for Natural Language Processing. And it will basically be able to come up with a sentiment score, how the tweet feels about a particular cryptocurrency. Okay, so we're short on time, so I'll let you read the code on your own, especially the things which are to do with the Stanford NLP. But the core part is really contained in the sentiment processor. So the DAG that we're going to build here is actually quite a lot more complex. So I hope you can see here that we've actually got the Twitter data source, which is something that has been written for this application. We add the timestamps to it, turn it into the relevant coins, calculate the sentiment score, and then basically output 3 different pipeline chains. Notice that this is very much a branching flow. So that actually we are taking data from a single source, but producing 3 separate outputs for it, which is more complex than the typical approach to Java streams. The DAG is a low-level API, so I won't show that in as much detail. We really want to focus on pipelines today. The 2 classes which support this are the sentiment processor and the stream Twitter key, and this basically is a processor which pulls all the tweets from Twitter using the official API. It's got some setup. You probably notice here that we've extended a class called abstract processor. This is how you create your own processors. We have an init method and a complete method, which are to do with setup and teardown, and then we basically just produce the close method from there. So the sentiment processor, likewise, is pretty simple, and it basically just produces a timestamped entry with a flat mapper to calculate the sentiment score. It's quite a fun little tool. If you've have some time to actually get Twitter credentials, then it's a good thing to run. Okay, so let's come back to Keynote, because I want to leave some time for questions. So one question which often comes up is, what's the difference between Jet and Spark? Well, Spark is kind of, I like to think of it as MapReduce 2.0. It's a great evolution of what Hadoop has done, and it has great second mover advantage. Its performance is much better than Hadoop. It does basically everything that Hadoop does, Spark does better. But the truth is that batch and stream technology are very different. They have different concerns. Hadoop and Spark, to a certain extent, are all about throughput. Stream processing really cares about latency. There are also some different technical concerns. There's the notion of locality. If you're processing a stream of events which have some dependency upon each other, it's kind of important that all of that processing happens on the same node. There's also this notion, which I think some people might have heard of what's called mechanical sympathy. This is the idea that to get the most performance you can out of a machine, you have to understand a bit about how the hardware works. It's something which very much has gone into the design of Jet, and Jet's kind of goal is to abstract the processing model away from the sources. So rather than being tied to HDFS or having to deal with HDFS as a first-class citizen, Jet wants all of its sources to be treated equally. Spark is also, I would say, somewhat moving in the direction of streaming, but it's still primarily a batch-orientated system, in my opinion, or micro-batch, I guess you could say. So the conclusions for that, like everything in software, is that it depends. If you have a super real-time need, if you want to determine, let's say, a fraud score and determine whether or not a transaction looks fraudulent in real time, then Jet is a tool which is going to be very much suited for that. There are also other concerns, as there always are. What's the current skill set? If you're a Java shop, then Jet has the advantage that it's very much a Java native technology. If you have some hugely complex deep learning machine system already with some vast data set and all the team already speak Scala fluently, well, you might make a different choice. But there are some really compelling reasons, I think, for adding Jet to your repertoire. Not least of which is that it's really very simple to start using it. You can just basically build a simple stream-enabled application very easily. Jet is just a library. It doesn't have a complex dependency. You don't have to sort of re-architect things that I've sometimes seen that we need to do for Spark. You can just basically dump Jet in as another Maven dependency, and away you go. The Pipelines API works really well, and yeah, it's a really good way to get started. There's a couple of slides here, which I'm just going to leave up for about 30 seconds or a few seconds each, just so the video stream picks them up. I'm not going to talk to these. These are some interesting points about the low-level technology, which I'll be happy to talk about in questions, but I do really want to get to the end. So that's the description of the vertices, how Jet's edges work, and some of the mechanical sympathy which goes into Jet. But I think at this point, I really should probably say thank you very much. And I hope you enjoyed it. And let's go to questions.
Hey there, Ben. It looks like we have a couple questions. One of the questions is, how does Jet relate to IMDG?
Okay, good question. So basically, IMDG is an in-memory data grid. It's a big cache. You can think of it essentially as being, well, don't kill me for saying this. It's kind of like a hash map which extends across machines. It does a lot more besides that, but that you can think of it in that way, so that you can just think of it as a big, useful map that you can use across a cluster. So it's like a cache or a non-persistent piece of data storage, if you like. It's not. You can do processing on it, and there are some great things you can do with it, but it's not fundamentally about processing a changing stream of data, whereas Jet is a stream processing engine. It's about taking sources of data which are either finite or notionally infinite, and just continuing to process them. And it's very much geared towards the processing of fresh items rather than the maintenance of a cache of data. I mean, both products are of course open source, but yeah, they should be thought of as distinct. They share a few internals, but not really anything hugely important. But yeah, I mean, you can use IMDG as a source for Jet, but it's by far from the only data source that it could use.
Great, thanks so much, Ben. Our next question is, what's the easiest way to get started with Jet?
The easiest way, if you just type Hazelcast Jet Maven Central into Google, it will give you the Maven Central stanza that you need for your dependencies. Put that in your pom.xml into your project, and it's like one jar, and it will pull down just a single small jar, and maybe there's one other dependency, but it's a really simple change to your project, and then you have Jet there as a library. One of the best ways, if you're already using Hazelcast IMDG, is to just add it to a project which has IMDG, and then think about, okay, I've got this data source. If you have another data source that's not MDG, great, it will also work there. What interesting things could I ask about? We've talked about the cryptocurrency sentiment. We've talked about a real-time risk assessment for a gambling application or a fraud detection, or a monitoring system for looking at how your web servers are responding in real time. There are all sorts of things that you can build. I think just thinking about what data sources do you have around, and then what can I spin up quickly with Jet to get answers to some questions, or just to explore my data set a bit more. That's really the easiest way, because that's one of the best things about it, is that it's a really simple, unopinionated API. It really doesn't want to get in your way. It just wants to be a useful part of your infrastructure to let you get on with solving your domain problem. So think of an interesting domain question, and then it should be hopefully very simple to get Jet to give you some quick answers to some simple questions about your existing data.
That's perfect. Thanks, Ben. And we're running out of time. I want to thank you, Ben, for a great presentation, very informative, and thank everyone for taking the time to join us for this Getting Started with Stream Processing webinar. Again, we'll be sending out an email with the link to the recording, as well as links to the resources shown in today's webinar. And then we can also get you in contact with someone who can help answer any of your specific questions relating to your environments. So again, thanks everybody, and have a great day.